This portion will now talk about the distribution of molecular velocities of gas particles in a given gas sample. Now, why do we need to understand this? That is, we have to ask the question, for example, if you have a gas sample, do all molecules travel at the same velocity? If they do not travel at the same velocity, is there a distribution of different velocities? It's like asking a question, if all the citizens of my town have the same amount of money in their bank account, for example. Obviously, the answer is very unlikely that they all have the same amounts. So then one would ask, how wealthy is this town? Then perhaps one could say, well, if I were to know the distribution of the amounts in the bank accounts of the citizens, for example, then we could perhaps estimate the relative wealth of the population of the town. So this is just an example to show how individual properties in a collection of objects could be quite different. And so in physical chemistry, we are very much interested in knowing how the individual is related to the ensemble. Ensemble meaning the collection. And so the given particle may be the slowest particle in the gas sample, or it could also be the fastest moving particle in the gas sample. And in general, we want to know how the velocities of molecules in my sample are distributed from, say, 0 to, say, a million miles per hour or whatever it may be. And so this is a very useful way to model the distribution of thermal energies in a gas sample, for example. The sample has a certain amount of thermal energy, and out of that, some molecules, a fraction of molecules, may have very high energy, and they may be able to carry out the chemical reaction we are expecting. And there may be a smaller fraction which do not have enough kinetic energy, will not be able to carry out the reaction. So as you can see, what we are talking about is the energies of molecules, because the velocity is a manifestation of its kinetic energy. And the kinetic energy can provide perhaps enough energy to activate the reagents to make products. So it's very relevant as chemists. We look at what fraction of the molecules that I have would have the necessary energy to produce the product. So in order to get to that sort of answer, we start asking questions about the distribution velocities. So first question will say, do all my molecules in the gas travel at the same speed? And very likely you would say, it's very unlikely that they all have exactly the same speed. Okay, then we'll ask the next question, how many of these molecules really traveling very fast above a certain speed limit? And how many are slowpokes? So this is kind of a question we are really trying to address. So we can now recognize there must be a distribution of velocities. And so how is this distribution? Sometimes it could be bimodal distribution, or it could be very sharp, or it could be very broad. And so we start asking very specific questions about what is the distribution, how the distribution changes with respect to the molecular properties, such as molecular weight, temperature, right, and pressure, and so on and so forth. Now recall that previously we have made an expression for root mean squared speed. And so that's equals to 3RT over m under square root. And so now we're talking about not the root mean square speed. We're asking actually what is the exact speed of my molecule. If I picked one out of a collection, what is the probability it will have a certain value? That's what we're asking. So if I randomly choose a one particle out of the sample, what would be the probability it will have a specific velocity, 1 meter per second, for example, in a given direction, or specific speed in any given direction. So we will say, well, let's try to get some mathematics into our discussion. And let's say dn sub c, be the number of molecules with the velocities in the interval c and c plus dc. What does that mean? It means that if I were to pick 1 meter and 1 plus dc meters per second, that is our velocity interval, then dnc be the number of molecules in that velocity interval, like that. So we're defining in general dn sub c being the small infinitesimal interval of velocity particles. That infinitesimally small interval of particles may have velocities in the infinitesimally small interval c and c plus dc. Okay, this is all for setting up for integration purposes later on. So there are a certain number of molecules in a small interval. That's the bottom line. Okay, so fraction of molecules in this velocity interval can be now written, because now we know the number of molecules in this small interval and we know the total number of molecules. So dnc divided by n, the capital N, which is usually the total number of particles in our discussions. So number of molecules in an interval divided by the total number of molecules. That gives me a fraction of molecules that are present in this interval we're talking about. So now if I were to take this fraction and we can rearrange it a little bit, and now if we divide this with the width of the interval, okay, so that is dnc by n. If I take that and divide it by interval dc, okay, interval dc, is the width of the interval dc, then I get dnc divided by n divided by dc. So what does that represent? That represents fraction of molecules in unit width of the velocity interval. Unit width because you're dividing with dc, the width of the interval. So that's now fraction of molecules present in the unit width of the velocity interval. It means the unit width is 1 meter per second. That is the velocity interval. So 1 over n multiplied by dnc by dc gives you the number of molecules that are present in a velocity interval of 1 meter per second out of the total number of molecules. Okay, out of the total number of molecules. So this is very important. Why we are doing this way? Well, we have expressions later on. We're going to show that this is what we really want most of the time in a unit width. Unit width, the fraction of molecules that fall in a unit width of the velocity interval, unit width of energy interval, a unit width of mass interval, and so on and so forth, depending on what is that is being distributed. I'll give you some examples at this stage. So let's first look at what we're talking about. You have a velocity in the x-axis. You have a number of particles on the y-axis. We have some distribution function. Okay. So on the number of particles, there is a tiny little interval dnc we have picked. And the velocity interval will pick a small interval dc. Okay. dnc is the number interval. dc is the velocity interval. So these are the items we just discussed. And coming back to fraction of molecules present in unit width is 1 over n dnc by dc. Now let's take a real life example. Let's walk into the grocery store. You see a bunch of tomatoes. Then you ask the question, well, it's unlikely that all the tomatoes in this basket have exactly the same weight. So then you ask the question, how is the weight of the tomatoes distributed within this box? Right? You have small tomato box, the big tomato box, the biggest tomato box, like that. The grocer has arranged it in certain price ranges. So then you ask, if I were to take a basket of tomatoes and weigh them individually, then I can plot how many tomatoes have a certain mass. Okay? So the number on the y-axis, number of tomatoes on the y-axis, mass per gram means the units in gram of tomatoes. And so you get some distribution function. I just drew some line here. What does this mean? There will be very few tomatoes that will have very low mass. There will be very few tomatoes that will have very high mass. Most of the tomatoes will be within certain range. And that range is used to fix the price. And so if this distribution is like this, very broad. That means the grocer hasn't really sorted them out in terms of its sizes. Okay, you have very few very small, but then suddenly it rises up, and then you have a lot of them of much larger weight and so on. Okay, so if it is, so you can see now how this sort of distribution functions are commercially very important, not just in physical chemistry. Okay, same with an airline, for example. And if you're able to fix the fare for a airline flight, then you want to know, let's say, what is the weight of my passengers? Okay, how does the weight vary from passenger 1 to 2 to 3 to 4? What is the distribution of weight? Because in the end, the fuel consumption depends on the weight that you need to carry from point A to B, and therefore your price will depend on the amount of fuel you want to burn, plus of course the time and other factors. So what fraction of my tomatoes weigh between x and x plus 1 gram? So that's an important pricing, and that's what we just wrote. That is 1 over n dnc by dc. What fraction out of the total number of things will weigh between one particular value of x and x plus 1 grams? So I'm writing x plus 1 because that's 1 unit. That's what, when you divide with dc in the top expression, that you're making that interval equal to unit width. Okay, unit width. So that's really important. And so this is how we're going to do all our fraction of molecules present in unit width of the velocity interval. That's what we're going to talk about from now onwards. So what fraction of tomatoes weigh between x grams and x plus 1 gram? So where we are interested in the unit width, not any arbitrary width. Okay, all right. So now let's take a couple more examples to look at this. Let's say you have a class and you get a certain score. If every student in the class got exactly the same score, then our distribution function will look like this, as a vertical line. That is the number of students and the score. All of them got the same score. So the height of this line will be equal to the number of students present in the class. Okay? So the score versus number. And that's how the distribution looks. Now if, let's say that no two students got the same score, right? And no two students, then it's going to be a parallel line to the x-axis. So because they all got the different scores, and so no two of them have the same score. Okay, no two of them have the same score. So you have only one person for each score. One person score one person score twice as much, one person score 3 times, 4 times, 5 times, and so on and so forth. So that will be a parallel line to the x-axis. If we have a distribution of scores in the class, then we can plot number versus score. Usually this looks something like this, a Gaussian distribution. There will be very few students who got very low scores. There will be very few students who will have very high scores, and most of them fit somewhere in the middle. And occasionally we also see bimodal distributions, and so that means you have two such functions overlapping on each other, slightly offset. Now let's do a simple manipulation. If I take the number of students on the y-axis and I divide with the total number, okay, number of students that got certain grade, divide the total number of students in the class. If I then plot that, I get something different. And this is the probability distribution function. Because if I divide number of students having certain grade, divide with the total, I get the probability instead of being actual value. Okay. That is, let's say that there are total of 10 tickets and you bought 1 ticket. Your probability of winning is 1 over 10. If only 10 tickets go to give rise to the lottery. And so if there are 1,000 tickets and you buy all 1,000, of course you're going to get you're going to win this lottery for sure. If there are 1,000,000 tickets in the lottery, you buy all 1,000,000, you get million by million is 1, so you get probability 1. If you buy only 1 ticket out of 1,000,000 tickets, your probability getting winning the lottery is 1 over 1,000,000. So the same way. So number of students who got a particular grade, divide by the total number of students, gives the probability the student might get that particular grade. So this is the distribution function. And I have now noted down again DNC, the unit and the small width of the the velocity, which instead of score, we write the velocity and x-axis in the previous slide. So DNP is the number of students scores B and B plus. Let's take a little more further into our example here. Then, so B and B plus, and let there be n is the total number of students present in the class. Then D and C divided by n gives me the probability of scoring B and a B plus. Okay. D and C is the number of students who got the scores, and divided by the total number of students gives me the probability that a student might get a B and a B plus. And so let's say if it is B and B plus is 80 to 85% for the sake of argument. Okay, 5% is the interval, B to B plus in the score, numerical score. So now if I divide D and C by n, right, with this interval, 5% interval, 85 minus 80 is 5%, 5. So if I divide this D and C by Dn, the probability of scoring, with the interval, then I get the probability of scoring that value per unit width, means 1%. So DNC by n times DC, okay, that gives me the probability that a given student may get 80 to 81%. Okay, so the probability of scoring in the 1% range, from 80 to 81%, is obtained DNC by n times DC. Here the DC is 5%. Thus, the width of the interval is unity for effective calculation of probability distributions. So this is very important. So not only we divide, right, with the total number of students present to get the probability, but that probability also needs to be divided with the width of the interval to get the probability within a unit interval.